Hello there my friends, welcome to our third lab. In this lab we are going to see the single-ended operation, double-ended operation and common mode operation of BJT differential amplifier, and we are also going to find the DC bias parameters, and we are going to also see the AC equivalent circuits of BJT differential amplifier. As we know, this amplifier is the first step before learning the op-amps, operational amplifiers. Now we will first find the DC operation parameters. Note that these two transistors are matched, they are identical. These resistors are also matched, they are identical. And we also know that everything is in ideal condition. So for DC parameter calculation, we will accept that the bases of these transistors are grounded. 0 volt is coming from here, 0 volt is coming from here. And here's the formula for finding the emitter currents, collector currents, and collector voltages, which are the outputs of this amplifier. And for this example, we have 9 and -9 volts as bias, and 3.9 kilo ohms for collector resistance and 3.3 kilo ohms for emitter resistance. Now, if we put these numbers into the formula, we will get these results. So let's check the simulation. We have NPN transistor, resistor, and sinusoidal source for our circuits. Also we have ammeters for measuring the collector currents, base currents, emitter currents. For adding these devices into the simulation, you first select component mode, then pick, then search for transistor, modeling primitives, NPN, and resistor, modeling primitives. Here's the resistor, and we assign in simulator primitives, and here is the configuration for this transistor. Either for beta is default. Now, if we simulate this circuit by pressing that button, okay, just ignore these scope screens. Okay, as in the formula, we get 3.49 milliamps from emitter. It's an approximate value, and 1.23 milliamps for collector current, and 4.19 volts for collector, as we found in the equations. And everything seems fine for DC parameters. Okay, let us stop the simulation. By the way, this is the DC generator that we added for this line. It supplies 9 volts, and another DC generator minus 9 volts. Also, we took that ground bus from this terminal mode from here, and these voltage probes from probe mode. Also, for ammeters, we selected these ammeters from this instrument, instruments menu. It was actually a DC ammeter. So for measuring the microamps, we double clicked on it, and display range will be microamps. Okay, what is the next? Now we should understand the AC equivalent circuit of this amplifier. Here's the general scheme of it, and here's the AC equivalent circuit of it. So for single-ended mode, we apply some voltages from one of the bases, and one base should be grounded, and here's the AC equivalent of it, and IB1 is equal to IB2, and let us call it as IB, and RI1 is equal to RI2, and it is equal to RI, and we mathematically assume that we have an RE resistor which is equal to Ri over beta, and here's the partial circuit for finding the parameters. And we assume that Re is very large according to the remaining resistors, and so we accept it as infinite. And here's the formula for finding the IB. So we know that beta 1 is equal to beta 2, and they are all equal to beta. And we found IB in here, and beta times IB is equal to IC, and IC is equal to VI over 2 times RE, and VO is equal to RC over 2RE times VI. And if we divide VO by VI, we can find the gain. And here's the last formula for finding the gain. Now, here's the example. Given that Ri1 is equal to Ri2 is equal to 20 kilo ohms, beta 1 is equal to beta 2, and they are equal to 75. So here are the resistor values, and here's the maximum value of that sinusoidal signal, which is 2 millivolts. And here's the IE calculation. It is 193 microamps. Here's the IC. As we know from the DC calculations, now we found VC as 4.5 volts, and we can calculate RE from Ri over beta, and also using the currents or resistors. So RE is also equal to RE over beta, which will be approximately equal to 269 ohms. So here's the gain calculation, and VO will be equal to 175 volts. Now let us look at the simulation. Here's a single-ended mode. Here's our sinusoidal source. Amplitude is 2 millivolts, and I took the frequency as 50 Hertz. It is not that important. For making the simulation work, I chose that value. And also we have a scope. Channel A is connected to the input terminal. Channel B is connected to Vout1, and channel C is connected to the Vout2. Now let us simulate it. Here's the single-ended scope screen. When we look at the yellow channel, yes, it shows the input signal, and for output we have much bigger voltage comparing to the input. We can include cursors, by the way. here we can put our cursor in here and another cursor in here. And as we can see, two outputs are very similar. We have the same voltage, however, they are phase shifted. We have the sum peak voltage value for the remaining output. So, what is the gain? 172 over 2, which is equal to 86. Yes, they are very close. Why is there this difference? Because for these transistors, VBE voltage is a little bit different. So, for single-ended mode, the results are satisfactory. Also, let's check out the voltages. We have 193 microamps for emitter, and we have 96.5 microamps for collectors, and we have 4.53 volts for collector. So the results are satisfactory, we can say. Now let us stop the simulation, and what is the next configuration? It is double-ended mode. For double-ended mode, we have two sources connected to the bases, and we have a differential voltage, which is the difference of the input voltages. And for this configuration, our I's are equal to 2 times beta times RE. For single-ended mode, it was equal to beta times RE. So, for that configuration, now we know that RE is equal to 538 ohms. However, for this configuration, if we make the calculations again from this AC analysis, we will find that differential gain is equal to RC over RE. So For this mode, we are applying 5 millivolts from this source and 4 millivolts from this source. They are in the same phase, don't forget. And if we divide 47 kilo ohms to 538 ohms, we will find that the gain is equal to 87.36. Now we will get this voltage if we do the calculations. So here's the double-ended mode. Let us close the single-ended screen. For double-ended, A and B are the inputs, yellow and blue. Okay, yellow is at this point, yellow is equal to the 5 millivolts, and blue is equal to the 4 millivolts. 4 millivolts. And the outputs are phase shifted. However, they have the same or approximate peak values. These small differences are not that important. We have 89 millivolts as a peak for this red channel. We have 84 millivolts for this green channel. So, what is the gain? The gain is approximately equal to the value that we have found in the formula. By the way, we have adjusted the beta value from this edit component screen. Don't forget, we can also adjust the remaining properties. So now let us check the common mode. For common mode, we will apply the same input from this side and this side, and here's the AC equivalent circuit of it. And now for this mode we have gain as this formula, and for our components, for R values, we find the gain as 0.54. And beta is again equal to 75, and Ri is the same. And here is channel A for input, channel B and channel C for outputs. And for common modes, the outputs, now they are not phase shifted. When we apply 2 millivolts to the input, we will get approximately half of the inputs. However, don't forget this gain is phase shifted, so we should put a minus sign for it. Okay, that's all for today. Thanks for watching and see you in the next lab. Thank you.